To provide a foundation for our results, let's begin with an overview of the key applications of BCI technology in the metaverse, categorized into medical and non-medical domains. BCI, as a technology that enables direct communication between the brain and digital systems, has diverse applications across these domains, with unique benefits and challenges. In the medical domain, BCIs play a transformative role in four primary areas. Rehabilitation and restoration. This includes assisting patients in regaining lost motor and cognitive functions, often through immersive environments and advanced feedback mechanisms within the metaverse. Health monitoring. BCIs provide continuous monitoring of brain and physiological signals, allowing for personalized healthcare interventions. Mental health. Here, BCIs enable cognitive and emotional mapping, which supports therapy for mental health conditions by facilitating immersive and interactive treatments. Diagnosis and treatment. BCIs aid in diagnosing neurological conditions and delivering telemedicine solutions, especially for conditions that benefit from direct brain-device communication, such as ALS. These applications are essential as they offer targeted solutions in healthcare, making treatments more accessible and potentially more effective, particularly when combined with mixed reality. On the other hand, the non-medical domain demonstrates BCI's versatility, expanding its use beyond healthcare. Here, we focus on three primary areas. Gaming and entertainment. BCI enhances the user experience by enabling direct brain-driven control, creating immersive and interactive gaming environments that respond in real time to the user's mental state. Transportation and navigation. BCIs are being explored for hands-free navigation, enabling people with limited mobility to interact with transportation systems in new ways. This can also enhance safety by allowing vehicles to monitor the driver's mental state and response times. Education and training. BCI technology can create adaptive learning environments that respond to the student's engagement level and cognitive load, making education in the metaverse more personalized and effective. This taxonomy not only highlights the scope of BCI applications but also underscores the metaverse's potential as a comprehensive platform for advancing both medical and non-medical fields. By integrating these domains, we envision a future where BCIs in the metaverse enable seamless interaction between individuals and digital environments. We're exploring the powerful applications of BCI technology in the field of rehabilitation and restoration, particularly within the immersive environment of the metaverse. BCI technology enables direct communication between the brain and external devices, making it an essential tool for various types of rehabilitation. This slide highlights key rehabilitation applications where BCIs play a transformative role, including neurorehabilitation, motor rehabilitation, robotic rehabilitation, cognitive rehabilitation, and remote rehabilitation. By integrating BCIs within a mixed reality setting, patients can receive targeted therapy that's both effective and engaging. In neurorehabilitation, the integration of BCI and the metaverse opens up exciting possibilities for treating conditions like upper limb paralysis post-stroke. Here, brain-machine interfaces, or BMIs, are utilized to re-establish motor functions, while motor imagery techniques are being tested for interventions in conditions such as Parkinson's disease. Furthermore, we see how combining BCI with robotics and VR can support spinal cord injury patients. By leveraging the immersive environment of the metaverse, patients can engage in real-time feedback-driven exercises that enhance recovery outcomes. Expanding on neurorehabilitation, VR and robotics provide robust support for BCI-based neurological recovery. By using pharmacological and neuromechanical therapies, the technology can stimulate neuroplasticity, essential for rebuilding lost neural pathways. An example here is AR-based robotics used to treat ADHD, offering patients a structured and interactive therapy environment. Despite these advancements, challenges remain, such as managing mental overload and scaling robot-assisted therapies to broader patient populations. Remote rehabilitation is another crucial area, where VR-based systems and telemedicine bring rehabilitation to patients' homes. For post-stroke patients, remote VR setups allow consistent practice for motor recovery, while electroacupuncture integrated with BCI enhances the therapy process. However, VR systems must be further developed to improve accessibility and usability, especially for telerehabilitation scenarios. This integration of telemedicine, VR, and BCI technologies not only makes rehabilitation more accessible but also provides real-time monitoring and adaptation. BCI's role extends into cognitive rehabilitation, where we leverage techniques like the discrete wavelet transform, DWT, for feature extraction from brain signals. Here, BCIs facilitate treatments that address cognitive impairments, especially for stroke-related challenges. Moreover, serious exergames and biofeedback mechanisms create interactive environments in the metaverse for cognitive enhancement. This approach widens the scope of cognitive therapies, though diverse technology requirements and limited use of deep learning remain barriers to overcome. Moving to motor rehabilitation, BCIs combined with visual systems can significantly improve motor recovery. However, research into AI-based methods such as linear discriminant analysis and support vector machines is limited. Additionally, the adoption of VR systems in motor rehabilitation can enhance efficiency, offering patients immersive environments that encourage consistent practice. Yet, expanding these applications requires more support for immersive VR and AI integration. In health monitoring, BCIs enable continuous cognitive and emotional tracking through technologies like neuromuscular models for personalized prosthetics. SEEG, or stereoencephalography, plays a vital role here by providing insights into cognitive and emotional states. While this offers tailored support for individuals, it also raises challenges, such as high technological requirements and concerns around data privacy. BCIs in mental health hold potential for immersive therapy by mapping cognitive and emotional states. Advanced neuroimaging technologies facilitate real-time feedback, creating personalized therapeutic environments. However, accessibility to these technologies and ensuring their real-time responsiveness remain significant hurdles, especially as we work toward widespread implementation. Finally, BCI technologies support diagnosis and treatment, particularly for neurological disorders. In the metaverse, telemedicine applications provide ALS patients with personalized medical care, establishing direct brain-device communication for treatment purposes. Nevertheless, challenges like the need for further research and improved integration must be addressed to make these treatments more accessible and effective. To summarize, this table provides an in-depth overview of various BCI applications in the metaverse across specific scenarios, advantages, and limitations. From neurorehabilitation to health monitoring, each application harnesses the power of BCI to enhance patient outcomes within immersive, interactive environments. However, high costs, technical complexity, and the need for extensive research are common challenges. Moving forward, addressing these limitations will be crucial for fully realizing the potential of BCIs in medical applications within the metaverse. Let's transition from medical applications to explore the exciting potential of BCI in non-medical domains within the metaverse. Here, BCI technology significantly impacts three key areas: gaming and entertainment, transportation and navigation, and education and training. These fields benefit from BCIs by enhancing immersion and interaction in digital environments. In gaming and entertainment, users can control avatars with thought alone, creating an entirely new level of engagement. Transportation and navigation leverage BCIs for hands-free control, supporting accessibility and enhancing safety. Education and training can use BCIs for real-time cognitive feedback, optimizing learning experiences. Let's delve into each of these categories in more detail. In gaming and entertainment, BCI technology enables users to engage with virtual environments in deeply immersive ways. Through motor imagery-controlled avatars, users can navigate VR games simply by thinking, opening up unprecedented levels of control and freedom. Furthermore, these immersive environments boost user motivation and engagement by responding directly to mental states. However, there are challenges. For example, managing cognitive load and ensuring sustained attention are critical to maintaining a seamless user experience. This intersection of BCI and VR has the potential to redefine digital interaction within entertainment. In transportation and navigation, BCI applications introduce tridimensional control systems that incorporate both emotional and navigational cues. Imagine navigating a smart city by merely thinking or managing your emotional state in real time. BCI and extended reality enable these capabilities, fostering new ways for individuals to interact with complex environments, particularly those with mobility limitations. However, there are still technical hurdles, such as signal processing complexity and human factors that affect usability. Despite these, BCI is paving the way for safer and more accessible navigation systems. Education and training are also enriched by BCI, especially in high-stakes fields like aviation. Using EEG metrics, BCI systems can monitor cognitive load, providing real-time feedback to improve performance and adapt training to the learner's mental state. Although implementing robust EEG and FNIRS classifiers can be costly and complex, the potential of BCI to revolutionize training experiences and foster deeper learning engagement is undeniable. To summarize our look into non-medical BCI applications, this table offers a detailed view of each category, outlining specific scenarios, advantages, and limitations. In gaming and entertainment, for instance, BCI-controlled avatars allow users to actively participate in virtual worlds. In transportation, BCI enhances environmental interaction and helps regulate mental states. Meanwhile, in education, real-time EEG feedback enhances training. While BCI applications are advancing, there are still technical and human-centered challenges to address. These limitations include managing cognitive load, ensuring precise focus, and overcoming complexity in signal processing. Looking at broader trends, we see that immersive environments are increasingly integrated into both medical and non-medical BCI applications. For medical uses, rehabilitation is the dominant focus, accounting for 86% of immersive BCI applications. Non-medical applications are led by gaming and entertainment at 53%, followed by education and training at 27%, and transportation at 20%. In the medical space, the growing emphasis on rehabilitation highlights a shift toward using immersive environments to enhance therapeutic outcomes. For non-medical uses, the focus on gaming and entertainment reflects the demand for interactive and engaging user experiences in digital spaces. Here, we see that virtual reality leads the way in medical BCI applications, particularly in rehabilitation, which represents 87% of VR's use cases. Smaller shares are allocated to diagnosis and treatment, mental health, and health monitoring. Meanwhile, augmented reality, mixed reality, and XR further emphasize rehabilitation, but also support health monitoring and diagnosis and treatment. This trend underscores the importance of immersive environments, particularly VR, in addressing medical needs effectively. Turning to non-medical applications, VR is primarily used in games and entertainment, which comprises 60% of VR's use cases, followed by education and training at 27%. AR and XR are also heavily focused on games and entertainment, with a secondary focus on transportation. Notably, education and training receive less attention in these immersive environments. For haptic feedback, we see a complete focus on games and entertainment, reflecting how sensory feedback amplifies user immersion and enjoyment in virtual experiences. These trends indicate a strong alignment between immersive technology and user engagement in non-medical fields. Finally, we explore how users interact with BCIs in immersive environments. First, enhanced immersion is achieved through EXG-based natural user interfaces within extended reality, which boosts user immersion and interaction, creating a more engaging experience. Next, Metaverse applications enrich 3D virtual spaces, enhancing both cognitive engagement and human-computer interaction. Simulation management improves the handling of complex virtual environments, making these spaces more satisfying and effective for users. Finally, user adaptability examines how well individuals adjust to BCI technologies in these immersive settings, a critical factor for user satisfaction and adoption. Together, these factors shape how we design and deploy BCI systems in the metaverse, ensuring they are both intuitive and powerful for end users. We dive into the breadth of research on BCI applications within the metaverse, as presented through a detailed categorization of studies. The tables compile numerous papers based on various parameters, showcasing a broad spectrum of use cases for BCIs across medical and non-medical domains. Here, we can observe how BCIs are used in conjunction with technologies like virtual reality, augmented reality, and mixed reality to create highly immersive environments. Let's start with the medical applications. In rehabilitation, many studies focus on conditions such as post-stroke recovery, spinal cord injuries, and neurological disorders. These applications often use EEG signals and paradigms like motor imagery or steady-state visual evoked potentials to facilitate motor rehabilitation and mental health monitoring. We see a range of devices used, from robotics to wearables, each tailored to the needs of specific limbs or motor functions. In non-medical applications, the focus shifts towards domains like gaming, entertainment, and training. These studies demonstrate how BCIs enhance the user experience by integrating emotional feedback and environmental interactions within smart city navigation and educational training. The use of paradigms like event-related potentials, ERP, and additional signal types such as electroencephalography, EOG, further enables intuitive and adaptive interactions within these immersive environments. These studies collectively highlight the versatility and impact of BCIs, emphasizing their transformative role in both healthcare and interactive digital experiences.